Welcome to the third part of first module of the subject REC. So students, in the previous session we have discussed reverse Carnot cycle, COP, and various processes involved in reverse Carnot cycle and the limitations that we face if we use reverse Carnot cycle as a cycle in refrigeration, right? So reverse Carnot cycle is an example for air refrigeration system. Now we will move to Brayton cycle or Joule cycle. Actually, this cycle is nothing but power plant cycle. So do you remember the process? There are four process. First one is isentropic compression, then what? Constant compression and expansion, then constant pressure, heat transfer, heat addition and rejection. So this is a cycle used in power plant, or this is a work producing cycle. So if we use this in a refrigerator, then the cycle will be reversed one, since refrigeration is opposite of an engine or power plant. Here in refrigeration we have to use a reversed pattern of Joule cycle. So I will draw reversed Brayton or Joule cycle. So this cycle is otherwise known as Bell-Coleman cycle. So please note it down. This is a cycle. This is a modification of reverse Carnot cycle. Reverse Carnot cycle is a basic cycle, or we will, due to certain limitations, we are going to modify this, modify the reverse Carnot cycle to a better cycle using air as refrigerant. That cycle is called Bell-Coleman cycle. So we'll draw PV diagram. Here, first 1 to 2 is adiabatic compression or reversible adiabatic compression or isentropic compression. So this is 2 to 3 is constant pressure heat rejection. 3 to 4 is adiabatic expansion. 4 to 1 is what? Constant pressure heat addition. So here refrigeration take place. So here P1 equal to P4, constant pressure process. Here P2 equal to P3, again constant pressure. So here heat will be added. So refrigeration, heat absorption. Here heat rejection, QR. Okay. So these two will be reversible adiabatic or isentropic process. So this will be compression, this will be expansion. Okay. So in I will show the same process in TS diagram, temperature entropy diagram. Temperature entropy diagram. 1 to 2 is isentropic process, so constant S. 2 to 3 is constant pressure process. So this will be like this. And 3 to 4 is again constant entropy, means isentropic heat addition. 4 to 1 is, sorry, this is isentropic expansion. Now 4 to 1 is constant pressure heat addition. So S1 will be equal to S2, S3 will be equal to S1. So here P is constant, here also P is constant. Constant pressure. So here heat will be added QA, here heat will be rejected QR. So the direction is anti-clockwise. If the direction was the cycle is flowing in anti-clockwise like this, here to here, 1, 2, 2 to 3, 3 to 4, 4 to 1. So this is reversed Joule cycle or Brayton cycle, also known as Bell-Coleman cycle. If the direction was clockwise, then this would have been the the Joule cycle, the proper Joule or Brayton cycle used in power plant. So how is this different from our reverse Carnot cycle? In reverse Carnot cycle, there were two isentropic processes, compression and expansion, but the other two, the heat addition was done using isothermal process, and heat rejection was also done using isothermal process. So two processes were having temperature as constant, but here heat addition and heat rejection are at constant pressure. Okay. So in reversed Carnot cycle, heat addition heat addition so in reverse Carnot cycle, heat addition and heat rejection were at constant temperature, isothermal process. Okay, both were isothermal process, but in practical cases, heat addition and heat rejection using isothermal process are very tough to do. They won't be possible that easily. So whenever there is a change in there is a heat transfer, it will surely will accompany with change in temperature. So isothermal processes reversible isothermal processes are not that easy to make possible. Okay, so in Bell-Coleman cycle, heat addition and heat rejection are at pressure equal to constant pressure process, isobaric process. So isobaric processes are easily attainable. That's not as tough as the case of isothermal process. So that is the main difference between reverse Carnot cycle and Bell-Coleman cycle. Both cycle work with air as the working fluid. Okay, so I will show the diagram representing the process. First we have the refrigerator here, refrigerator or the space to be cooled. From space to be cooled, it will undergo an isentropic compression using a compressor. Okay. After compression, after air getting compressed to a higher pressure and higher temperature, it will reach a cooler. So in cooler, what happens? It rejects heat to a cooling fluid. Okay, cooling water in, cooling water, wait. So in, out. So cooling water in, cooling water out. So the air at high temperature and pressure rejects heat to this cooling water, and this cooling water extract heat from that air and go out, and and it will undergo some cooling from another cooling tower and come back to again extract heat from this air. So the air will become what? The pressure remains constant, temperature gets lowered, and low temperature, high pressure. So here it is 1, 2, 3. Now after 3 it will reach an expander, so it will become 4. Here expander means it reduces temperature and pressure of that air. Then it again enters a refrigerator. So low pressure, low temperature air is ready to absorb heat from the space to be cooled. Then this air will again get heated. The temperature increase, but pressure remains constant, since this is a constant pressure. Here P equal to constant, here also P equal to constant. Okay. Here S equal to constant, entropy remains constant. Here also S equal to constant. So this high temperature, low pressure air is again compressed to a high temperature, high pressure air, which again comes to cooler. So the cycle repeats. So from here Q get absorbed, here Q get rejected, right? So this is the process. So this is the process of refrigeration. So air absorbs heat from the refrigerator and undergoes a cycle and rejects heat to the cooling water. So this is how refrigeration takes place. Now we have to get an expression for what? COP. So students, you know COP of refrigerator is nothing but heat absorbed by heat rejected minus heat absorbed, right? So here heat absorbed is from the process 2 to heat is getting absorbed in the process 4 to 1, right? 4 to 1. So in 4 to 1, since it is a constant pressure isobaric process, isobaric heat absorption. So Q4 to 1 can be written as how? Cp into T4 minus, or T1 minus T4. T1 minus T4, right? So Q41 or Q absorption is nothing but Cp T1 minus T4 kilojoule per kilogram of air. So the unit will be kilojoule per kilogram of air, because I'm not using m here. So that is why the unit is kilojoule per kilogram. Okay. Now what is Q rejected? That is in the process 2 to 3, right? 2 to 3 you will get Cp T2 minus T3. So T2 is higher temperature, T3 is lower temperature. Qa equal to Q421 equal to Cp T1 minus T4. So here T1 is higher temperature, that is why T1 minus T4. Here T2 is higher temperature, that is why T2 minus T3. Okay. You just have to take since we have to get a positive value for heat, we are taking higher temperature first. Okay. Now we got the equations. Now how can we write COP of refrigerator? QA is nothing but Cp T1 minus T4 by Cp T2 minus T3 minus Cp T1 minus T4. So you can cancel Cp. So what remains is COP R equal to T2 minus T1 minus T4 by T2 minus T3 minus T1 minus T4, right? Now you can simplify this. How can you simplify this equation? I will take T4 common. COP equal to, I am taking T4 outside from the numerator. It will become T1 by T4 minus 1 by, here I will take T3 outside. T2 by T3 minus 1 minus again T4 outside, T1 by T4 minus 1. Students, the process 1 to 2 is isentropic process or adiabatic process, right? Adiabatic, reversible adiabatic, reversible adiabatic process, compression, right? Similarly 3 to 4 also is reversible adiabatic expansion, right? So students, for an adiabatic process, the PV relation is PV raised to gamma equal to constant, right? All right. So this is the relation between T and V. So what is the relation between P and T? Pressure and temperature. Do you know? Pressure and temperature is related like 1 minus gamma into T raised to gamma equal to constant, right? Otherwise P1 1 minus gamma T1 raised to gamma equal to P2 1 minus gamma T2 raised to gamma, or T1 by T2 raised to all raised to gamma is nothing but P2 by P1 all raised to 1 minus gamma, right? Or T1 by T2 all raised to gamma, equal to P2 by P1 all raised to 1 minus gamma by gamma, right? Otherwise T1 by T2 is equal to P1 by P2, and this minus 1 minus gamma becomes gamma minus 1 by gamma. So here it was P2 by P1. So to make P1 by P2, I will put a minus here. I will put a minus for this 1 minus. Students, COP of refrigerator we have written like T4 outside, T1 by T4 minus 1 by T3 into T2 by T3 minus 1 minus T4 into T1 by T4 minus 1. So this is how we have written. Now we know that process 1 to 2 is isentropic and 3 to 4 is also isentropic. So for 1 to 2 we can write it as T1 by T2, or we can write T2 by T1. T2 by T1 equal to P2 by P1 all raised to gamma minus 1 by gamma, right? Or T2 by T1 equal to P2 by P1 raised to gamma minus 1 by gamma. Similarly for 3 to 4, T3 by T4 equal to P3 by P4 gamma minus 1 by gamma. So these two processes are isentropic process. So this is compression and this is expansion. But we know P2 is equal to P3 and P1 equal to P4. Since process 1, 2 to 3 and 3 to 4 are isobaric process. So P2 equal to P3, P1 equal to P4. So here P2 and P3 same, P1 and P4 same. So this means this whole term and this whole term are same only. It means T2 by T1 is equal to T3 by 4. T3 by T4. T2 by T1 equal to T3 by T4. Right? So I will rearrange it as T2 by T3 will be equal to T1 by T4. So applying this equation in our COP equation. Our COP equation was T4 T1 by T4 minus 1 by T3 T2 T2 by T3 minus 1 minus T4 T1 by T4 minus 1. So T1 by T4 is equal to T2 by T3 equal to T1 by T4. So these three terms will get cancelled. What remains is COP of refrigerator is equal to T4 by T3 minus T4. Or I will take T4 to the denominator, 1 by T3 by T4 minus 1. See, 1 by T3 minus T4 minus 1. COP of refrigerator is 1 by T3 by T4 minus 1 means this will be equal to 1 by P3 by P4 all raised to gamma minus 1 by gamma or minus 1. That is COP of refrigerator. So students, P3 by P4 is equal to P2 by P1 itself. Since P3 and P2 same, P4 and P1 same. So COP can be even written as 1 by P2 by P1 whole raised to gamma minus 1 by gamma whole raised to minus 1. So this can be termed as a particular ratio. Since this ratio is equal to this ratio, I will use a term called RP, pressure ratio. Pressure ratio RP equal to P3 by P2 equal to P3 by P4 equal to P2 by P1. So COP of refrigerator using Bell-Coleman cycle is RP raised to gamma minus 1 by gamma whole raised to minus 1. COP of refrigerator is nothing but 1 by RP raised to gamma minus 1 by gamma whole minus 1. So this is the equation for COP of refrigerator in the case of Bell-Coleman cycle or reversed Carnot cycle.